I want to talk about the following representing frames as Möbius transformations or equivalently complementing quaternions with a measure for deformations. So I thought about what to talk about, and I had a talk lined up that would contain all the hot topics that would make me look like a researcher that's looking into problems that have relevance for future blah blah. It would contain 3D printing and augmented reality, virtual reality, mixed reality, and all that. And then I decided it's kind of, I mean, you know all that, and I feel as an academic I should rather try to convey one simple idea that can actually be useful when you're trying to implement things. So the idea I'm going to present is one small nugget that can be very useful when you're trying to bring geometric ideas into the computer for actual programming. So let me ask, who has heard of homogeneous coordinates? I had hoped, okay, so, and I hope those who are not raising their hands are just too lazy, right? So I guess most of us have heard of homogeneous coordinates, and they're not just a funny concept from projective geometry or affine geometry. They're actually really, really useful for day-to-day computations. We all need them every day when we do computations for 3D. And this will be less useful. It doesn't have as broad as applications, but it still will be useful, and it's kind of a similar concept. Along the way, I will also explain what quaternions are, because I expect, while many of you know what quaternions are, maybe not everybody knows what quaternions are. Okay, let's go. So, frankly, I don't really need a motivation, but I want to give you one. We want to build structures. So this is related to Helmut's talk. Structures where three beams come together in one joint. And what we want to do is we want to characterize these joints, right? And I will call these joints a frame. And my example that is more visual than the slides is this. This is what I want to talk about. And the point is, I don't care about the length of these sticks, right? What I do care about is that these three sticks come together in one point. And what I want to characterize is two things. Number one, I want to characterize the orientation of these three sticks. And it's well known how to do that. We will just rediscover that. And more importantly, I want to characterize this part down here, right? And I call this the shape. So orientation of this changes by a rotation when I just move it, right? So this is a rigid transformation. And I could also make an effort now and change the shape by a deformation. I won't do it, right? But if I pulled with enough force, this thing down here would change its shape. And the goal of my talk is to find a nice representation for the shape and a meaningful way to characterize how much deformation was necessary to go from one shape to another. Okay, so that's the goal. Let's go. The first observation is, if I do not care about the length of these three sticks, I might as well put this center here into the origin of a coordinate system, and I might say the sticks have unit length. Okay? I don't care about the length of the sticks, so I make them unit length. If all three sticks have unit length, these 3 points are on a common sphere around the origin. So basically, I will kind of forget about my sticks, or you can think of, I will intersect the 3 sticks with a unit sphere, and I will take these intersection points. That is characterizing the orientation of this thing and the shape. So from now on, I want to talk about 3 points on a sphere. And of course, when I say from now on, I talk about 3 points on a sphere, I will tell you in 2 minutes that I will talk about something else. But for the moment, let's think of these 3 sticks as points on the sphere. And just as a small detour, I guess for many of you, when you hear frames and 3 sticks in 3 space, you're thinking of linear transformations. And this doesn't work. It does work when I have the freedom to say these three sticks should be orthogonal, because then they actually do span R3. They span the space. I might have 3 points that are in a common plane with the origin, right? I might have these 3 flecks basically on one large circle on the sphere. Then they don't span R3, and then there is not necessarily a linear mapping from this system to any other system. So linear maps don't work. We need something else. So what we're going to do is we leave this picture of the sphere, and we're going to project the points on the sphere into the plane. So I have my sphere over here. I take the North Pole, and I shoot a ray from the North Pole through the tip of this point into the plane, and that gives me a point in the plane. And for convenience, I'm using points in the complex plane. So I'm using complex numbers now. You can do all of this without complex numbers, just using 2 real numbers, but it's getting a bit messy, right? Or depending on for my taste, right? It's messy. So let's do it with complex numbers. And so this is just the equation. Oh, by the way, I should say, yesterday I liked when Yaron said, it's going to be a bit technical, but don't worry, it's only images. I would have to say, it's going to be a bit technical, but don't worry, it's almost all equations, right? So, but the equations are really simple. So you can just lean back and be happy that all the transformations are really, it's immediately clear. Okay, so we take these points on the sphere, we project them to the plane. Now we observe one thing. This is not necessarily a complex number that's finite, right? If we have one point on the North Pole, it will project to infinity. So now we're happy. As a computer graphicist, I'm happy because I know what to do. I'm using homogeneous coordinates, right? So I represent everything not as one complex number, but as 2 complex numbers. And the mapping usually goes like this. You take your complex number, which is a point in the plane, and you add this 1. Now you have 2 complex numbers. And homogeneous coordinates just means I identify points with lines. So any 2 points are equivalent if they are a multiple of each other. So 2 points are equivalent if there exists lambda, and lambda is a complex number now, such that 1 is just the multiple of the other. Okay, just homogeneous coordinates. For those of you who haven't seen this, why is this useful? So 0 just goes to 0, 1, very simple. 1 goes to 1, 1. And this North Pole up there, which would go to infinity, let's say it goes to lambda 1, and in the limit, lambda will be infinity. Now we use this little trick. Lambda 1 is the same as 1 and 1 over lambda, right? I just divide both numbers by lambda. And now it's easy to take the limit. The limit's just 1, 0. Okay. So basically, this trick of using homogeneous coordinates just means I can represent every number, right? And I can deal with infinity in a decent way. Okay. Good. Now let's go back to the problem. Our problem is we have one such system of 3 sticks, which are 3 points in the extended complex plane, and all of them I can represent by complex homogeneous coordinates. And I have another set of 3, and I'm looking for a mapping that maps one to the other. And I'm lucky, the easiest possible mapping that I can think of is doing the job. So what's the easiest mapping I can think of? It's a linear mapping. So I take my homogeneous coordinates for this point, and this point, and this point, and I multiply them by a 2 by 2 complex matrix. And if I do the counting, this matrix actually has 8 degrees of freedom. 4 complex numbers, 8 degrees of freedom. I'm mapping 3 points in the plane to 3 points in the plane, so I need 6 degrees of freedom. But wait a second, this exactly fits because we're in homogeneous coordinates, right? So this 2 by 2 matrix defines a mapping only up to these multiplications by a complex number, right? So I'm losing 2 degrees of freedom. So this mapping exactly has 6 degrees of freedom, and I need 6 degrees of freedom, and they all work. And they work also if the 3 points are in collinear. Okay? Because I have the freedom to scale this matrix, I say it should have unit determinant. Okay? So I say, and that's true, any 3 points, as long as they're distinct, map to any 3 points, and I can describe this mapping by a complex 2 by 2 matrix, and I ask that the matrix has unit determinant. And that's not unique. I still have m and minus m, but that's a detail. Okay. So because we're in homogeneous coordinates, this is a projective transformation, and these projective transformations are called Möbius transformations. Okay. So basically up to here, what we have established is this system of 3 sticks goes to any other system of 3 sticks by a Möbius transformation. And Möbius transformations are these complex 2 by 2 matrices with unit determinant. Now, okay, good. The program now is, we want to characterize these transformations. Essentially, we want to see what is a rotation, and then, once we understood what is a rotation, we can look for what's the rest, what's a deformation. Okay. My plan is, I first do this for the rotations, and my hope is what we will end up with is, you're familiar with that, right? You will see something that you've seen before, so all these steps are not surprising to you, and then I want to do the same thing with deformations. Okay. So this is the setting. I have tried to draw a rotation here, so my frame of 3 elements is just rotating, and I'm looking at what happens to these 3 points in the plane. And now, what happens is maybe not surprising. I could try to prove it. I will just state it. This 2 by 2 matrix, this complex 2 by 2 matrix, will be a unitary transformation. And unitary transformation just means if I multiply this matrix with its conjugate transpose, I get identity. It's kind of the complex counterpart to orthogonal transformations. Okay. And now we're doing simple technical steps to see something here. Okay, so all these matrices I can write in this way. I can write them based on 2 arbitrary complex numbers, alpha and beta. And then in the lower row, on the diagonal, I have the complement of alpha, and here I have minus the complement of beta. These are all the matrices that satisfy this condition that U times U conjugate transpose is identity. Okay, now I'm doing something very simple. I'm just writing out these 2 complex numbers in kind of the standard way, right? I write them as alpha is just, say, x0 plus x3 times imaginary unit, and beta is x1 plus x2 times imaginary unit. Simple, right? So then I immediately know what minus beta is, a minus beta conjugate, and conjugate alpha. I take this number, and its conjugate is obviously just taking the plus sign and making it a minus sign. And now, I'm telling you, right, this is so easy that it can't get any easier, right? Okay, now I'm putting this into the matrix, and I get this matrix. So all the rigid transformations are matrices of this type, and obviously, they're controlled by 3 real numbers, x0 to x3. Now I will take, say, 90 seconds to rediscover the quaternions. It took Hamilton like decades to find them, so let's take 90 seconds to find them. We don't really need them, but it's so cool that it now takes only 30 seconds that we better do it, right? So let's see. This matrix is obviously just x0 times identity plus x1 times this matrix, a 1 here and a minus 1 here, plus x2 times i's on the off diagonal, and x3 times I and minus I on the diagonal, right? That's just the matrix that's there. Now, for fun, let's take the square of this matrix, and we'll see that this matrix squares to minus identity. And again, for fun, let's square this matrix. And again, it squares to minus identity. And this matrix squares to minus identity. And now let's take the product of this matrix, and this matrix, and it also multiplies to minus identity. And this is exactly the quaternions. So for those of you who knew the quaternions, these are the quaternions, right? So we've just rediscovered the quaternions. Kind of, we knew that before, but okay. But here they are. Okay, fine. Ah, right, I forgot this. So here are the quaternions. Now, what we really need is just this one condition. We said these matrices should have unit determinant. So let's compute the determinant of this matrix. It's just x squared plus x0 squared plus and so on equals 1. What does this mean? This vector x is a point on the sphere. And this is nice because it means we can easily measure the distance of points, right? A simple space, a simple metric space where we can measure the distance. And how do we measure distances on the sphere? We take the Euclidean inner product, and we know it gives us the cosine of distance, right? And for unit quaternions, we actually know we can take a unit quaternion, and we look at its first component. So basically, we're taking the inner product with respect to the origin, and it gives us x0, and that's the cosine of half the rotation angle. And maybe a little lesser known fact for unit quaternions is you can take any two unit quaternions, take the inner product, and you get cosine of half the angle that's necessary to go from one orientation to the other. Okay, fine. So many of this, I think, was known to most of you, and I just took this kind of line of thought to do the same thing for deformations. Last thing, geometric meaning. x0, as I just said, related to angle, and the other three, x1, x2, x3, are actually the axis of rotation, and this axis of rotation depends on a reference frame, right? I need to pick some reference frame, and then x1, x2, x0 give me the axis of rotation, but it's relative to the reference frame. Okay. Good. So now, the plan is to do the same thing, but for deformations. I will go a little slower now, because I would think this is new to more or less everybody. Okay. Deformations. My claim is we get everything that's not a rigid transformation by taking this mapping M that maps from here to here, the Möbius transformation that maps between any two sets of frames, and multiply it with its conjugate transpose. Okay. Why am I hopeful that this is a good idea? Because if I compose my arbitrary transformation with a unitary transformation, a rotation, and I take this product with its conjugate transpose, I multiply out this u, now it appears here, and it, oops, and I fall, and the unitary transformation goes away. Okay? So what does this mean? I can take my transformation M, I can compose it with any rotation, but the rotation doesn't appear in my matrix H. Right? So this matrix H is independent of any rotation that's inside this Möbius transformation M. So this is the right thing to do. This is, of course, I mean, this is more of a trying to convince you. You can also argue more formally, and then you would argue based on how M acts on the group and so on. But believe me, it's the right thing to do. Okay. And now we do the same trick that we did for discovering the quaternions. We just look at this matrix H. What property does H have? It's Hermitian, right? Because I generated it as M times M conjugate transpose. So it's the equivalent of a symmetric matrix for complex matrices. So I can write down any Hermitian matrix like this. Here on the diagonal, it has two real numbers, and I write them as H0 plus H3 and H0 minus H3. And here it has two elements that are conjugate transpose of each other, so I write them as H1 plus IH2 and H1 minus IH2. Okay? These are all these matrices. And you can say, okay, I could have written this differently. I could have written the two real numbers differently. But I tried to kind of follow the thing that was useful for the rotations, right? I basically said I want to write it as h0 times identity plus and so on. Okay. I mean, even if you disagree that this is the simplest thing to do, you agree that this is a way to do it. Okay? Now let's put in the unit determinant condition. If M has unit determinant, so does H. And we compute the determinant, and we find the determinant of this is H0 squared minus the other things squared. Right? So it looks very similar to the case for quaternions, only these components, H1, H2, H3, they now have minus signs. What does this mean? Every such matrix is a point on a hyperboloid. Okay, so I can identify each of these matrices H with a point on the hyperboloid. For the quaternions, it was a sphere, right? Every rotation was a point on the sphere. Every deformation is a point on the hyperboloid. Okay, very nice. Now, how can we measure deformation? We need to acknowledge that this is a hyperboloid, right? And then we need to take the right inner product with respect to the hyperboloid, and the hyperboloid is, of course, hyperbolic space, so we take the Minkowski metric, right? So we take inner products of these points H with, say, in this case, the origin. Only the inner product now has a different signature, right? And not surprisingly, the signature, basically you've seen the signature, it looks, in terms of plus and minus signs, it looks like this, right? So we take this inner product with this signature, and we get the hyperbolic cosine of distance. And the important thing now is, this is invariant to transformations, right? If I measure deformation in this way, I can do it relative to any reference frame. So far, I have said I compute this Möbius transformation that goes from here to here, then I take the Möbius transformation, multiply it with its conjugate transpose, and then I can look for the origin of the system. I take Minkowski inner products, and I get hyperbolic cosine of the distance. Fine, but this reference frame identity is not necessary for this game, right? I can also map these 3 points to a reference frame and get some representation M relative to the reference frame, and then I form some matrix H. And I can take these 3 points to the same reference frame, get some other transformation M prime, and then some other representation H prime. And now if I take these 2 vectors H and take their Minkowski inner product, then I still get the same deformation, right? So I can measure deformation of 2 frames, and my measurement of deformation is independent of my reference frame. So this was basically goal number 1. Okay. What does it mean? It means my original goal of characterizing the shape of a joint, this thing down here, right, this thing that defines how this looks up to rotations or up to orientation, this means I have now found this. It's a point on a hyperboloid. I can specify some reference frame, and then I can put every such joint onto the hyperboloid, and I can measure deformation as the distance between these points on the hyperboloid. And every joint shape is a point in hyperbolic space. Okay. Now, is there a geometric meaning? And geometric meaning of these coefficients, H1, H2, H3, depends on my choice of reference frame. Right? So let's pick a nice reference frame. And I suggest to pick as a reference frame the flat, threefold, rotationally symmetric frame. So I get this frame if I take these 3 sticks, I push them down into the plane, and I make sure the angles between each two sticks is 120 degrees. Okay, so this is my reference frame. Now let's see what happens if I look at certain shapes in this reference frame. This is the flat symmetric reference frame. Now, let's look at any rotationally symmetric, any frame that has threefold rotational symmetry. So like almost these three flags. Rotations are not relevant, so I can always align them with my flat frame. Right? I can always make sure that these three sticks are kind of symmetric to my flat symmetric reference frame. And then I see that in the plane, these points that I project into the plane are just an isotropic scale of the flat symmetric reference frame. So basically, it's kind of clear, right? I took this flat, I had made this thing flat and symmetric, and now all I do is I pull all three sticks up by the same amount. And these are all symmetric reference frames, because I didn't care about orientation. So symmetric frames are isotropic scaling. And that means I can write them down. They all look like this. They have zeros here, which means they don't have H1 and H2 components. So all the symmetric frames are represented by vectors that look like this. They have two zeros for H1 and H2. So in this embedding space for the hyperboloid, there are a plane, right? They are on the intersection of the H1, H3 plane with the hyperboloid. And now, what's the rest? The rest is flat frames. And so all the remaining frames are flat frames, and what I see is I don't scale, I just shear. All the flat frames are shears, so they all look like this. They have the same entries on the diagonal, which means they don't have an H3 component, so all flat frames look like this. So again, I have found geometric meaning in the coefficients. For the quaternions, it was x0 was the angle, x1, x2, x3 were the axes. Here it's H3 is symmetric frames, H1, H2 flat frames. Okay? Now, one cool thing, this you can skip, right? And it's maybe a bit technical, but you can project onto the closest flat frame, or you can project onto the closest symmetric frame. It's very simple. If you want to project onto the closest flat frame, you just set H3 to 0. You just remove H3, and then you have a flat frame, and you project back onto the hyperboloid, and you have the closest flat frame. And likewise, you can project onto the closest symmetric frame by zeroing H1 and H2. This is kind of cool for us in graphics because we use these projections onto frames quite often, right? These orthogonal projections. And that also means you can directly measure distance to symmetry. So you can come up with a measure for symmetry, and it looks like this. Basically, it's measuring the distance to the closest symmetric frame. So you can compute for any frame this H vector, and then you can say this is a measure of symmetry that is invariant to rotation. It will directly tell you how threefold rotational symmetric is my frame. And likewise, you have a measure for flatness. You can project onto the closest flat frame, and you get this distance. So based on your vector H0, 1, 2, 3, 3, you get directly that this measures how flat is your frame. And you can rewrite it like this. So this is your measure of flatness. Basically, H3 is directly telling you how flat is my frame. Okay. I found this was really beautiful, right? I was surprised. I mean, maybe for some, so of course not my idea, I have to say, right? I have a co-author who's in math, and he told me this, right? And he said, we can't publish it in math, it's not, of course, not written down in math, right? I mean, that would be too easy. You could just read it and use it. But it's kind of known, more or less, yeah? people in math often say to me, it's well known to those who well know it, right? And it's so well known that they don't bother writing it down. So we wrote it down because it was useful for us, because basically what we wanted to do in our application was to do exactly this. We wanted to measure how flat is a frame or how symmetric is a frame. And basically these are the formulas we needed. Okay, now for computations, what we do is we turn these frames that we have in Euclidean geometry into points in hyperbolic space by what I just told you. We perform computations in hyperbolic space. We measure distances. We compute means. We can do K-means in hyperbolic space. And then when we have these results, we turn the points in hyperbolic space back into frames in Euclidean space. And in this way, we can loop over this, and we can optimize frames with techniques that are known. Just one remark. The way from frame to point is just exactly what I have told you. We take the three sticks, we make them unit vectors, we stereographically project, we compute the transformation M to some reference frame, we compute H based on M times M conjugate transpose. We extract this vector H from this matrix. So this step is simple, and now if you look closely, it could be that the way back is more complicated, but luckily it's not, right? So the way back means we have this vector H, we can form this matrix, and now we need the Möbius transformation that corresponds to this matrix, and all Möbius transformations that correspond to this matrix are the square root of H times an unknown rotation, right? There could be an arbitrary amount of rotation, and we don't care about the rotation. So the tricky part could be this, the square root of H, right? Square root of matrices. Not clear if this is easy, but for 2x2 matrices, it's very easy. And for 2x2 matrices with unit determinant, it's even easier. So the square root of H is proportional to H plus identity. So the way back from these matrices H to Möbius transformations is as simple. We just add identity. Then we get the Möbius transformation, we apply it to the reference frame, then we have our Euclidean reference frame. And then I want to use the last maybe 5 minutes, 3 minutes, to just show you some applications that we did, but my hope would be that this is a useful tool, like quaternions are a useful tool for many, that this is a useful tool that you could use to measure shape of frames and deformation of frames. So what did we do with it? We dealt with meshes where every vertex has degree 3, so dual triangle meshes, hex-dominant meshes. And we optimized how the three edges came together in these frames. And so what we did here is we optimized for symmetry. And down here, we optimized for planarity. And interestingly, we don't understand really why. When we optimize for flatness, we'll get these indented hexagons that Helmut had just shown. But the funny fact here is we optimized for the planarity of the three legs coming together in a joint. We did not optimize for the hexagon to be flat, right? And the hexagons are not flat, because if everything was flat, this could not be, right? So, but still, the hexagons have kind of the same shape. So I don't know why, but maybe there's a deeper reason, or it's just coincidence. What we also did, what was one of the original aims of this project, was to do Kmeans. What's the reason? This has to do with architectural applications. We felt if we can build this frame structure and the joints just come from few classes, we can generate molds for these joints and mass produce the joints. It's very expensive if each joint is different. It's probably much cheaper if they're just 5 different joints. So in this example, we were just using 3 different joints. Here we're using 5 different joints, and we're using 7 different joints. And all the joints have the same shape, they're just oriented differently, right? And we achieved this by doing standard K-means clustering, but in hyperbolic space. And it's very simple to do K-means clustering on this hyperboloid. I can't go into the details, but it's surprisingly, it's not more complicated than doing it in Euclidean space. Okay. A curiosity that I want to show you, optimizing for symmetry is actually very restricted. Optimizing for symmetry is more restricted than optimizing for flatness. And you will see, if you optimize for symmetry, the degree of the faces. So here we optimized all frames to have this, to be rotationally symmetric, and then the face degree shows up. So in this example down here, you see how the pentagons come out. So of course, in that scenario, face degree relates to curvature. Okay. So to conclude, the shape with which three sticks or beams come together is a point on a hyperboloid. That's the right picture. These points encode symmetry and flatness of how these three sticks come together. Computing such points from the three sticks is easy, and also computing three sticks from one such point in hyperbolic space is easy. And the hyperbolic space is useful because we can measure distances between points, and that's the amount of deformation that's necessary to go from one shape to another. Okay. And with that, I'm done, and I thank you very much for your attention.